Assalamu alaikum students and welcome to another lecture of Slate. This is Khawaja Yasin. Let's study chemistry. In the previous lecture of ionization energy, we talked about a few factors of ionization energy. We talked about the definition. We talked about the equations of ionization energies. And we further talked about the factors which impact the ionization energy. Now we are going to talk about the successive ionization energy and the trends. We talked about the trend across the period and we talked about the trends down the group. But now let's talk about the trends across the periodic table, like what happens to the first ionization energies. Remember, we mostly talk about the first ionization energy only because with the second ionization energy, things change. For example, if I have to tell you, the first ionization energy of sodium is simple, but the second ionization energy of sodium ion will be too high. Why too high? Because sodium ion has a noble gas configuration. On the contrary, if I'm talking about magnesium, magnesium will have a first ionization energy value and that would be a normal value. We will just talk about the values later in this lecture because you do not need to memorize the values they're given. So, first ionization energy of magnesium, second ionization energy of magnesium, ion. This will be magnesium's monopositive ion. It would be a little higher, but not too high because this is still not a noble gas configuration. But the third ionization energy of magnesium is from a noble gas configuration. Students, that will be too high. So that is why we cannot compare sodium and magnesium together on the basis of their second and third ionization energies. We'll be stuck to the first ionization energy. That is something you should remember always. Now, let's talk about what happens in the periodic table. Generally, we know across the period, the ionization energies increase. That is something we know. But just look at this one. As I said, we only talk about the first ionization energy values. So this is the first ionization energy. And look at the graph and the trend. What is happening here? Initially, we have hydrogen. That's the first ionization energy of hydrogen. You don't need to memorize K 1000. If it falls in 1000, it falls in 2000. We don't need to memorize that. But from hydrogen, there is a huge jump for the first ionization energy of helium. Then down we go, obviously lithium. Before that, let's see this trend again. From helium to neon to argon. Decrease in ionization energy. Why? Because this is down the group. Likewise, if we notice from lithium to potassium, then there is another decrease here. Because down the group it's decreasing. That is one thing. And we remembered across the period it increases. Across the period it increases. Across the period it increases. Now that I would say the trends that we studied, these are general trends. Like general trends are the ones without anomalous behaviors. There is no anomaly, there is no off the book, there is no difference there. So generally, it increases across the period. But let's see what's happening here. This is a very important graph that is mostly going to come in your exams, mostly with the same type of questions. So they may ask you, why is there a general increase in across the period? You will just write this answer. that across the period the nuclear charge increases, the shielding effect remains unchanged, and the radius decreases. Same thing. If they ask you, why is there a difference between helium from neon to argon, you will talk about the down the group properties, the factors we talked about in the last lecture. But let's notice what's happening here. From lithium to beryllium, there is an increase, but beryllium has more ionization energy than boron. There is one difference. From boron to carbon, there is an increase. From carbon to nitrogen, there is an increase. But from nitrogen, after nitrogen, it's oxygen. Oxygen has a lesser first ionization energy. And fluorine has again higher. If we notice at the period 3, from nitrogen to magnesium, it's sodium to magnesium, it's increasing. From magnesium to aluminum, there is another decrease. Then silicon is higher. Then phosphorus is higher. Then sulfur is again lower. There is the same trend happening. Same trend. Third group. Sixth group. So this is again third group. This is sixth group. And according to the new periodic table, A levels, 13th group and 16th group. Now what is happening? So let me tell you, boron is not going off the charts. Boron and oxygen are following the same trend. If you look through this, boron will have it here, carbon will have it here, this will have it here. Oxygen, but nitrogen should have been here somewhere below oxygen, and beryllium should have been there below boron. So the anomalous behavior is shown by these peaks. Not the ones with lower ones, but the higher ones are going in a different way. Likewise, magnesium and phosphorus are going differently. What is happening? For that, we need to talk about the electronic configuration. Let's look at that. We have beryllium. One is 2, 2 is 2. And then we have boron, 5. 1 is 2, 2 is 2, 2p, 1. If I compare this with magnesium and aluminum, they are the same. 12, aluminum 13. So with magnesium, we can take neon as the noble gas, the checkpoint, because according to the shorthand formula, we follow the noble gas. So after neon, magnesium is 3s2, and aluminum after neon is 3s2, 3p1. The same configuration, difference of shell number. So what is happening here? If we look at the concept that we talked about in the previous lectures, that this is partially filled and this is a fully filled s orbital. But that is not the reasoning that you are going to give in the exam. This is, you would know the concept that it is partially filled, that's fully filled. But why? Why is partially filled stable, unstable, and why is fully filled stable? Because we are removing the outermost electron. Here, we are removing electron from 2s. Here, we are removing it from 2p. So why does B has ionization energy higher than beryllium? That's a fixed answer. As in beryllium, we are removing the electron from 2p orbital which is higher in energy than 2s orbital. That we know. S has a lower energy. And it is difficult to remove electron from a low energy orbital. So here we have a clash between S and P. Here we're taking out electron from the S, and here we are taking out electron from the P. So P has a high energy orbital, is a high energy orbital, so it's easier to remove. S has a low energy, so it is difficult to remove an electron from lower energy orbital of S. Therefore, more energy needed for removing electron from 2s orbital. So this is a comparison of P and S. If you get a question of magnesium versus aluminum, the answer will be the same, but you would just say 3s and 3p. That's how you're going to distinct it. That's it. Now, this is fixed. That answer, that question is most probably coming in your CIs. And you have the fixed answer. Either you're going to get this question, or they would ask you between nitrogen, oxygen, and phosphorus, sulfur. So let's draw nitrogen. One S2, 2S2, 2P3. 1s2, 2s2, 2p4. Let me make the p orbital here. So that is the electronic configuration here, students. In nitrogen, that's how the 2p orbital is. And in oxygen, that's how it is. Same is the case with phosphorus and sulfur. Neon, 3s2, 3p3. Neon, 3s2, 3p4. We have the same electronic configuration here as well. So why? So more difficult to remove. Now going back to the previous concept. This is partially filled. This is completely filled. That's fixed for us. So what are we going to do here? We are not going to talk about partial and complete filling. Rather, we need to understand the concept. Here we have an electron pair as well, while there is no pair in nitrogen. And due to the electron pair, we will experience repulsion. So the concept is called the electrons in the 2p orbital of oxygen are experiencing spin pair repulsion. This term is very important. This is a fixed answer. Fixed answer. They're experiencing fixed spin pair repulsion, due to which it becomes unstable and it is easier to remove the electron. While there is no spin pair repulsion in nitrogen or phosphorus, they're easy. We have spin pair repulsion in sulfur and oxygen. So they have lower ionization energy values because it destabilizes the system. These are fixed answers, my students. Almost every year you will get a question like that. That is one. Now, we will talk about successive ionization energies of an element. We can easily identify through the graph or through the values about the group number or the identity of an element. For example, let me draw the graph myself. In the exam, you're going to get such a graph. Here we have energy on y-axis, which is increasing. Now we are asked to identify what element it is. So let me show you how to do that. You will get such a graph. What is happening here? They will ask you to identify the element. These are successive ionization energies of an element. And we know ionization energy, successive ionization energies like one from another one increases. So we start from here. So what do we witness first? That we removed 1, 2 and 3. We just removed 3 electrons. Uske baad, we have a big jump. Why is there a big jump? Shell change. And here we have, after removing 3 electrons, we attain noble gas configuration. So we attain a noble gas configuration after removing 3 electrons. So 1, 2, 3. Then there is a big jump. We see the jump here. There is a shell change. Then we see another shell change here. But after how many ionization energy values? 1, 2, 3, 4, 5, 6, 7, 8. So they are slightly increasing across the period. And there is a big jump. And then there are 1 and 2. So what is happening here? These levels, they talk about periods. So this is the first period, second period, third period. And the dots are the ionization energy values. But first ionization, second, third. So what does that mean? Before getting a noble gas configuration, before attaining a noble gas configuration, 3 electrons were removed. So that means element is in group 3. So group 3 because 3 electrons and 1, 2, 3, 3 periods. So 3 periods, third period and the third element. So this is aluminum. Third period, third group. So that is all for today. In the next lecture, we are going to solve some past paper questions, students. And we are also going to see how when you get the values for ionization energies, of successive ionization energies. How do you find a group number? Because obviously, if there is a general increase in values, for instance, for the first value, I have 500 kilojoules per mole. Second must be, these are hypothetical values, 1100. Third, 1800. But the fourth ionization energy, students, that may go up to 5200, 3 to 4 times higher value. That's a major jump. And if you witness the values after 5200, it would be 5900 or something, smaller increase. So when we witness a big increase here, that means that's the separation. So before that, we were in one shell. So 1, 2, 3. So even the ionization energy values tell you that before the jump, major jump, whatever is the number of ionization energies, that is the number of electrons in the outermost shell. Hence, that is the group number. So thank you so much, student, for being here with me. See you in the next lecture. Take care and Allah Hafiz.